Okay, hello and welcome to my channel. Today we're going to be talking about the quantum harmonic oscillator and continue the last two videos. Today we're going to move on to the next method, that is the ladder operator method. So here we're going to utilize these operators that we have in our quantum system to figure out what our energy eigenstate would look like and how you would evolve it. Okay, so first let's take a look at our Hamiltonian in the harmonic oscillator, which is this x squared. And here, what you would want to do is that you would isolate these the operators. Yeah, you isolate the operators. Yeah, that get an x squared, x squared plus p squared m squared omega squared. Okay, so oh my god, 1/2 m omega squared. Sorry. Okay, so once you isolate your operator out already, what you would want in your Hamiltonians is that when you factorize it, so you factorize, you would want your Hamiltonian to be a combination between, well, I would call this operator the a dagger a plus a number. When you factorize your Hamiltonian, you would want it to look something like this. And you see we have this term that we can expand it even more. So here we'll expand it. Can you write that? And you see this, you can expand into, well, a plus ib times a minus ib, and that would be the and usually that would be the end of it. But here we gotta consider, when you do that, you put them together again, there would be two terms that are xp and px that wouldn't cancel out because we're dealing with operators instead of numbers. So that would create a commutation. So this is equal to xp omega ipx. So you just do the thing after you do this after you do this. You do that and you what do you call that? Distribute these in, you would get that. Okay, it looks a little bit messy. Okay, plus. Okay, now this term plus p make it square. Right, so from this, now you see you can put these two together and that create a commutation. So now you rewrite it like this, plus an I over m omega commutation x and p. There we go. And remember, the commutation of x and p is equal to IH bar. That IH bar, I would create a minus. So what you get here, after all, is a minus H bar over m omega. So you put it back here, it would look something like this. So from the Hamiltonian, gonna put it back No. Before we put it back, let's assign a dagger and a for our terms first. So this term can be rewritten as, well, we just expand this final term that we have, and this you can say can do that as well. IP M omega. Right, so you can see that this looks very similar to this. So you can assign this to be our A dagger and this to be our A. Okay, that might be a little bit confusing as we're gonna use A and A dagger later on. So let's say this is U. Yeah. We're gonna assign this to be U dagger and that to be our U. And that would be our number that we needed right here. So when you sub it back into our Hamiltonian, what you would get is U dagger U plus the there you go. That would be what you get. Okay, now we can move on and consider the commutation between our U and U dagger. So the commutation, gonna write it up here, U dagger would be the commutation between this and that. So X plus IP over M omega X minus IP over M omega. And from this, you can see that X and X commute and P also commutes. So what you would get is this term and this term. So this term, and commutation between X and P give you IH bar. So the commutation of P and X would give you minus IH bar. Okay, so when you expand this, would be X. Yeah. Use the linearity to expand this. XP. This is PX. And our last one is minus. It's a minus. No, it's a plus. Of P and P. Right. So expand this term is 0. This term is 0 as well. We leave us with these two. So do the calculation would use you 2 H bar over M omega. 2 H bar. Okay, I'm gonna erase this part and just write our solution. Right, and now we're gonna put it back to our canonical commutation relation by setting this to be equal to 1. So we're gonna put this in here, distributed. So we have to root. So we root our term U to put it into the commutation. There we go. Now you can get the canonical commutation relation by doing that. And when you do that, this term and this term is, well, called, this is A hat, and this is A dagger. So these are called ladder operators, or a cooler name for them is the annihilation operator and the creation operator. So these will have some very interesting properties, as we will find out later on. Something stuck to my feet, sorry. Okay, so once you got your new operator, you would want to, well, put your old operators in terms of these new operators. So let's start with x. Our x would be, I think, h bar 2 m omega a plus a dagger. P is this a dagger minus a. Well, you're gonna use this a lot, so it's good to remember these. And what else do we have? Yeah, no, you only have to know these for now. Okay, next is V dagger and V. That would give you 2h bar m omega a hat a dagger. V dagger V give you 2h bar a dagger a. And your Hamiltonian now is gonna be, this would lead to your Hamiltonian being this, just 1/2, right? So once you have your Hamiltonian, you're gonna ask, well, we can't really find a definite bound for this, so we're gonna have to use an inequality to evaluate our expectation value for the Hamiltonian. So somewhere to, this part can be gone. So I'm gonna write the expectation value of our Hamiltonian as this. Well, if you don't remember, this notation means that this is the bra side and this is the ket side. And together, when you do this, it means this. And so just a note on the notation that I'm going to use here. It's not that confusing, and you apply this, you get your two sides, the operator side and the constant side. And what is this? See, a dagger here can be moved over here to yield you an a hat, since this side is the complex conjugate of the ket side. So when you move it over here, move your a dagger over to the bra side, that would turn into an a hat. Okay, so we can say that this guy, an inner product, is always going to be greater or equal to 0. And this guy, they're the same, so assume normalized, this would be greater or equal to 1. Therefore, this has to be greater or equal to h bar omega over 2. Right, so we got our inequality, and assume that your lower bound is known. So when lower bound is known, that would result in your energy of ground equal to h bar omega over 2. And that is exactly the same as the number method that we did 2 videos, in the last 2 videos. Okay, so from that, you can say that now when you act your annihilation operator on the function now, it would be equal to 0. Therefore, I should write that. All right. So your annihilation operator is that guy, the x plus ip omega on side 0 is equal to 0. Okay, and now you can see the wonder here that we kind of did, that we go from a normal time independent Schrodinger equation would have the second order derivative, but now to get this ground state, we only have to deal with the first order derivative. So that is just so much more convenient on our end. So now you just isolate the derivative, and so you do this by moving everything else on the other side. Is there an x? Yes. Yeah. Okay, so that is what you got. Now you put this in the exponential form, and you would get here to the m omega for 2h bar x squared. And you see that this guy is exactly the same as what we found when using the number method, but way faster, right? The last time we have to do all sorts of stuff just to get our thing that we need, which is minus u squared over 2. But this time we can get this pretty fast, and just think A is, well, your A here for the ground state is this guy. Yep. Okay, and I guess that's it for today's video. Next time we're gonna take a look at some properties, some commutations of these newly found operators. Okay, so I guess that's it for today. Goodbye.